All right, example number 8 now. So we have a picture of a potter's wheel over here on the side, but essentially what we have is a disc that's rotating. Let me draw you a quick little picture of this. So it's basically just a disc that's rotating around, like something like this. And so let's just write down some information that we know. We know that the mass of this disc is 40 kilograms. We're given the diameter of it is 0.5 meters. That means essentially that the radius is then 0.25 meters. So this is r in here, by the way, right? And we're told that it starts from rest. So that means that the initial angular velocity is 0. And it reaches a angular velocity of 80 RPM, revolutions per minute. And it does this in a time period of 1.28 seconds. All right, and we're asked to calculate a bunch of things. So this is all our given. In part A, we're asked to find the rotational inertia of the system. Part B, we're asked to find the torque, or the net torque of the system. Part C, or actually this is not part E. I had removed some parts that were on content we haven't covered yet. We're just simply asked to find the change in angle. Okay, so first, solving this, we are needing to find the rotational inertia of the system, which is simply a disk. So if you go back earlier in your notes, all right, when we talked about disk, all right, we're looking for something that looks like that. That's a solid cylinder or disk. So the formula for that is 1/2 mr squared. So that's what we're going to be using to calculate the rotational inertia of this system. So our rotational inertia is going to be simply 1/2 mr squared. So 1/2, the mass is 40.0 kilograms, and the radius is 0.25 meters quantity squared. All right, so if we put that into our calculator, all right, we're going to get 1.25 kilograms times meter squared. So that's part A. For part B, kind of similar to the last problem, we're finding the net torque, but we can't calculate it by using R times F, right? We can't use the torque formula times sine of the angle. We have to use really Newton's second law. Sum of tau equals I times alpha. We've just calculated I. We now just need to find what alpha is. So what is the angular acceleration? Remember, that's the change in angular velocity over the change in time, or the final angular velocity minus the initial angular velocity divided by the time interval. Again, we have a little bit of an issue where things are written not quite in radians per second, so we have to convert RPM to radians per second. So we have 80, remember the final initial angular velocity is 0, 80 revolutions, instead of writing RPM, I'm going to write revolutions per minute. All right, we're going to need to convert that in a minute. I'll put that over here. The time interval is 1.28 seconds. All right, so revolutions. In one revolution, there are 2 pi rads. And also I need to convert minutes. I'm going to shift this over here because I didn't have enough space. So I need to also do another conversion here. I need to get rid of minutes. So in 1 minute, there are 60 seconds. So minutes go to the top, and so we can cancel out here. We're going to cancel out the minutes here. We're going to cancel out the revolutions here. And so we're going to get basically radians per second for our answer here. So 80 multiplied by 2 pi divided by 60 times 1.28. Pulling out my calculator, I get basically 6.54 radians per second squared. So now, all we need to do now is essentially plug that into this equation right up there. Plug that into here and here. So the torque on the system is going to be I times alpha. I is 1.25 kilograms times meter squared, and alpha is 6.54 radians per second squared. So plugging all that into your calculator, you get a net torque of 8.18 Newton meters. And yes, the problem's not done because it looks like we're going to do some reviewing here because we're asked to find the revolutions that it makes in that time period. That's nothing to do with torque, really, and this unit that we're doing on dynamics. It's just a review of what we've done with angular kinematics, right? So lots of ways of doing it. Since I know the acceleration right now, I'm thinking of just maybe using this equation, theta equals theta initial which you'll assume is 0, plus angular velocity initial times time, again, that's 0, plus basically 1/2 alpha t squared. So it's just really 1/2 alpha t squared. So the final theta will be 1/2 times the angular acceleration, 6.54 radians per second squared, multiplied by my time interval of 1.28 seconds. That's being squared. And our angular position is, pulling my calculator, 5.36, radians. Now, I see my answers in revolutions, so how do we convert it back to revolutions? That's again, well, in 1 revolution, there are 2 pi rads. So we divide by 2 pi, and that gives you 0.853 revolutions. That's it for this example.